Okay, so maybe I try to explain again the logics. So you have been assigned to groups. This worked to some extent well last year. And the intention is really meant, A, for you to get to know each other. Secondly, then for the exercises, that means the notebooks, and then also actually the computing exercises, that you work together and basically work on the exercise and the notebooks together in a group. So you always with 5 other people. So we have now 6 groups of 6, a very nice number. And if you need to talk to each other, then with the exercise, it's always the first row turns around and can talk to the row afterwards. So this is how you're oriented, because behind you, there's always your corresponding partners. Except the first row, they are excluded with this exception. You're not allowed to do. Of course, if anybody is welcome, he can do the exercises. I'm very happy. The other point is there are thankfully people from the CCQ that will help you, that first of all check that our exercises make sense. I hope they do. That they can be solved in finite time. I hope they do. And they were so nice to really help you. So if there are then questions when you do the exercises, please also, it's me and all the other lecturers, but also the teaching assistants, please just say hello. Thank you. And then exactly. So they will, if you have questions or just any other thing, they will also help you. And if there are other problems, please come to us. But at the beginning, I will do some normal, straightforward lecture. But I think this will change throughout. So we heard already in the morning, very nice talks by Angel and Professor Kono about why light matter interactions is interesting, specifically in the strong coupling regime, specific in the setup of collectivity. And now in this afternoon session, I would like to basically go back to the very basics and talk about the fundamentals of this ab initio school. So the idea, and as also Angel has pointed out, if you start somewhere in the middle, you might lose certain details. So in the idea of not every model is wrong, but some are useful, what we would like to have is a coherent theory that really starts from very, very basic principles. And on these principles we want to build, and we want to follow through all the possible approximations through that we know we don't miss essential physics. That's why today, or in this afternoon session, which will be 2 hours, I only give you the essentials. I will not give you the Hamiltonian that we work with, so the Pauli-Fierz Hamiltonian that was briefly flashed, but I will tell you how it can be assembled. So what are the basic ideas that go into it? And that means which ideas should be reflected in any other Hamiltonian. So assembling these bits and pieces, I will do tomorrow. In the morning session there, we'll show you the Pauli-Fierz Hamiltonian. That is, to our understanding, the best starting point for really mathematically well-defined theory of light matter interactions. And we will build on that in the following days on several levels of simplifications to really get down to the point where we can do actual simulations and calculations. All right, so that's the goal, the goal of today, to give you the basics. But before, I would like to do a recap. And here I will be, again, relatively brief, because you already got access to the GitHub before, and there were lecture notes that I hopefully all of you took a look at. And even if you didn't take a look, most of what I tell you should have been covered, with the exception of this least point, this third point. what are the problems when you couple light and matter. But what the first part of my talk or my lecture will be basically just recapitulation of very, very basic things that you probably have seen in your lectures already. That is, we recapitulate very basics electrodynamics and use it to calculate one thing only. We will recapitulate basic quantum mechanics. We do the same thing. We use it to calculate one thing only. And then we try to connect it. And we will see that there are a lot of problems that appear. Because the issue is that underlying this distinction between electrodynamics and quantum mechanics is our perception that somehow we have a separate theory for light, which is electrodynamics, and a separate theory for matter. And of course, the question is, so you have two theories seemingly disconnected. How do you connect them? And it's not only my intention to show you how to connect them, but to also show you that at least on the theory side, the distinction between light and matter is not so clear. This is a choice, and it's a theory choice. So you can change what you call light and what you call matter. And that's very, very important to also understand these strong and ultra-strong coupling situations. All right, so let me see whether we'll succeed. So this is the learning objectives of the first part. You can also essentially take the third point of piquing your interest, theoretically spoken, to say, okay, it's worthwhile to go back to the basics and try to understand where our notion of light and matter comes from and how are they connected. All right. Theory of light. Everyone will have seen this theory in one way or the other. The most famous formulation of the Maxwell's equation is this one, given in terms of B and E fields. And there are very many other formulations that are equivalent. So it's not that they do something different, it's just a different formulation. And we will also use at least two other formulations. And you will see that the other formulations of the Maxwell's equation come in handy, not only to do calculations, but also conceptually, right? But this is the standard form of the Maxwell's equation as we know them. And I just want to point out that, okay, what one usually does then in the lectures is one solves these PDEs in some way or the other, approximate to get a feeling how light behaves. You have electrostatics, you have magnetostatics, and so forth and so on. But the main point is, what is often not stressed enough, but important for us here, is that these equations come with an important consistency condition, namely that the source term, so this is a charge current, right? We know that radiation comes from charges. This is a charge current, so it flows somewhere through three-dimensional space, and we have a charge density. Your Maxwell's equation only makes sense if this consistency is fulfilled. So you already see just from standard Maxwell's equation, the first course that you take on electrodynamics, the matter cannot be anything. It has to fulfill this continuity equation. You will see this continuity equation come up all the time, and that's really the most important ingredient in light-matter interactions for a lot of various reasons that I hope you will understand. All right, so that's basically the thing that one does in electrodynamics in one way or the other. Now, I said there are many different types of formulations that come in handy. Let us give a different one. This is very important, often called macroscopic Maxwell's equation, which you will also use on Tuesday and also afterwards, sometimes in practice, because you can do a lot of practical things. We will also use them for practice. And again, these macroscopic Maxwell's equation are not new. They are the same Maxwell's equation as the one above. They are just a different type of bookkeeping, because you now say I have rho and J. These are the physical things that you can see and measure. And I divide them in two pieces that I cannot measure. This is a theory choice, right? You say I have bound charges. I describe them with a polarization field yet to be defined. That's auxiliary quantities here. They are not physical, right? It's just I arbitrarily decide these things I call bound, these I call free. Of course, the rationale behind there, coming historically from the fact that people saw bound state system behaved somehow differently than free space system. They did not yet have a theory like quantum mechanics or microscopic quantum theories. So this is basically the rationale why they do this division. So you introduce these auxiliary fields, P, the polarization, M, the magnetization. And accordingly, you just, since this is a linear equation, so you can just change, shift stuff around. So it's just a renaming. I don't do anything different. You introduce new auxiliary fields, D for displacement, P is the polarization one, and here H is the magnetizing field and M the magnetization. The physical fields are these ones. These are just auxiliary fields. But using these expressions, you can, for instance, here write the Ampere's law in this way, and here the Gauss law. Now, why do we use it? Well, sometimes it makes calculations easier, okay? So we will use it to actually see how would we determine or how would we define an absorption coefficient, right? Propagation through a medium, that seems to be an important thing, and that's of course connected to spectroscopy. And we make the assumption that we say the free charge, there are no free charges. Now you rightfully ask, what does this mean? I don't know. I didn't give you what I mean by free and bound charges. This is just bookkeeping. I just throw this out. I don't care. The only physical thing that I do here is that there is no magnetization, meaning the magnetic field will basically not be disturbed. It will just go through as if in free space. That's an approximation here that will not be true in general, but that's the only approximation I make here. Then I plug this into this equation. So I basically just use now that M is 0. So that means H will just become B, and then J free is 0. So this is a linear equation. That's then basically what I get here, because here it is written in terms of the displacement field. Again, the displacement field can be written in terms of the physical field and the polarization, which is an auxiliary field. It's a lot of bookkeeping back and forth. So we just do it because that's the standard way. And then we apply two things. We do the time derivative thereof. So that's why we have here second order derivatives. They clearly come from here. And then we apply a very important identity. So because basically, if we go back here, you can connect the time derivative of P with the curl of E. So what you get here is basically 2 times the curl. And you have a very basic relation in vector analysis. And you have to remember that now we talk here about 3-dimensional fields. This is a vector Laplacian. This is not the scalar Laplacian you use in quantum mechanics. There will be a consistency. They need to agree in a certain sense, but this is a different type of relation. And this relation will also be extremely fundamental in electrodynamics. You will see where it comes from, because it comes from very, very basic ideas in electrodynamics. So we use this, so that's why we write the 2 curls into basically a vector Laplacian and this divergence term. Then this is a PDE. PDEs are hard to solve, but we can do again a trick. We do a Fourier transform in time, in space. Why Fourier transform? We assume that all our fields decay when they go to infinity in space. So they are square integrable. This is the underlying assumption. That's why I can do a unitary Fourier transform. And in time, we do a Laplace transform. Why a Laplace? Because it's an initial value problem, right? Here, you need to actually set what is your initial state. Sometimes you also hear the other way around that they say you do here also Fourier transform, and then you add an eta, which is a dissipation term. But that's just a simple, different way of saying, yeah, you do a Laplace transform, right? Either ways, doesn't matter. You do these 2 tricks. You can also just interpret your Laplace transform with a dampening term if you, your Laplace transform is a Fourier transform with a dampening term if you want, but you get an algebraic equation. The next thing I do is I say we are thinking about traveling waves. So we are used specifically from quantum mechanics to think mainly about electrostatics. And statics means usually longitudinal fields that if they move or propagate, then it's in the direction of the polarization. So K is basically the momentum, or K is the K value where it propagates to. And traveling waves, so electromagnetic or electrodynamic waves are perpendicular, so transverse. So this is 0. And we get a very simple relation. But the problem is we never specified what P is, right? I did now just shift stuff around. So what gain do I have? I want to close these equations, so I need to get input for something that tells me how do my bound charges react. Now comes the definition of what I mean with bound charges. That's the first time I talk about it, right? I talk all the time about polarizations and blah, blah, blah. I never told you what it is. Now I have to specify it, and it is a choice. Here, there is no unique way to do this. I choose it. In electrodynamics, this is called a constitutive relation. You can choose any you want. Of course, it's a good reason why we use it, and we will explain why a little bit later. But in the end, what you have here is the macroscopic response. And it's important. We usually tend to think about these fields here on a macroscopic scale. So you really come in with a field that you can actually see, or if it's in a different wavelength, then you don't see it necessarily. But the things that you probe are macroscopic usually. You don't usually probe a single atom or a single molecule. You probe an ensemble of atoms, an ensemble of molecules, or even worse, a solid state system. This is a huge thing, right? It has a macroscopic response, right? We see it here, or we can look through the window. This is the macroscopic response that we can perceive. So this is a macroscopic object, but we just still assume for simplicity that there's this linear relation, which again, what I put there under the hood is that my light field will not change my matter system. It will only let it wiggle around a little bit, but it will not change its states. That's the basic assumption that goes in here. There can be no change by this relation. I did here a trick. This chi AA is basically saying the response in one direction. So I apply a field in one direction, and how does the same reaction react? I assume here for simplicity that my system, think really about an ensemble of molecules or atoms, is homogeneous and isotropic. That's why I have a 1/3 here, and that's the relation. And that's, of course, where quantum mechanics comes in, right? Or if you want to do classics, a classical description. This is the response of your macroscopic ensemble. Not yet specified, we specified in the next step. But with this relation, we choose this linear relation because then it's easy to solve. We can just get this dispersion relation, and then we can get this alpha of omega, which basically just tells us how does the electric field decay while it penetrates our ensemble. And again, this is a well-known result. It's the imaginary part of this macroscopic response function, right? So this is basically how it absorbs. This would be the calculation you do to, for instance, give an experimentalist an absorption spectrum. So how does an ensemble of molecules or atoms absorb? And this works pretty well normally. Okay, nothing new, just recapitulation of the basic ingredients that we have in electrodynamics. Now, we need to think about where do we get this? Since we want to do QED, so some quantum thing, we will use a microscopic description of matter, that is quantum mechanics. And of course, quantum mechanics, we usually choose just the usual Schrödinger equation. We will have NE electrons given by their position and their spin, so their spin 1/2. And then we have NN nuclei also given by their position and spin. And then you have to solve this other PDE here, where the static equation or the static Hamiltonian is the well-known Schrödinger Hamiltonian. I will discuss tomorrow why we focus on the Schrödinger Hamiltonian for several reasons. First of all, a practical, and secondly, also a mathematical one. So we could do Dirac, but there are some reasons why we don't do it. So I will not introduce Dirac to then remove it again. That's why we just get stuck with the usual Schrödinger equation. An important thing here, these are the kinetics, and very, very important if we talk about QED. these are observable masses. So in your quantum mechanics, these masses are what we measure. You will see in QED that's not the case. So keep this in mind. We will also learn how we get this equation and also the Maxwell equation back from QED, and which level of assumptions and approximations we put in if we use such an equation or the Maxwell's equation, right? So we turn it around. Right, this is the usual Schrödinger equation. You have here the charges of the nucleus and ions. And then you have usually some external field. Again, here, electromagnetism seems to be just an external quantity. So this is an external field that propagates through, will not be absorbed. There are no photons, right? And the usual assumption is that this is something like in dipole approximation. Here, this is electric field that couples basically the total center of charge of the nucleus and electrons. So this is the way how it couples to the electrons. This is how it couples to the nuclei. Nothing new, again, all of you have seen this, probably solve this type of equations every day. But a first important thing to realize is, even without this external field, this equation does not have a ground state. Very easy to see. If I rotate this Hamiltonian, I get back the same Hamiltonian. If I translate everything, I get back the same Hamiltonian. It has at least 2 continuous degrees of freedom. This Hamiltonian only allows scattering solution. It means non-normalizable solutions, right? If you really want to talk about eigenstates that are normalizable, you need to do something different. This is an old problem in molecular physics that I don't go into detail. We follow the usual ways, and depending on what we want to do, we will take different routes. For instance, if you want to do thermodynamics, quantum thermodynamics in that case, you will put everything into a box with finite volume. Well, the volume is an extensive property, so it has to be finite. And you have to choose boundary conditions, at least for Hamiltonians of this form. Then you can prove mathematically that you just have normalizable states. So then you suddenly have a spectrum, and that you then use to build up your partition function. In our case, which will also be discussed in much more detail on Thursday by Ite, who is making pictures back there. Hello, Ite. In the context of light matter interactions, is the Born-Oppenheimer approximations, I call it, because there's also a lot of story behind there. I just make the simplest type of argument that there's a lot of details under the hood. I just say, well, let's assume that the ions or the positively charged particles have a mass that is much, much larger, set them to infinitely strong or infinitely heavy. Then you get to the Born-Oppenheimer approximated Hamiltonian. That's the Hamiltonian you usually solve in quantum chemistry or solid state physics. It's already approximation to the Schrödinger equation here. And this is the electronic structure Hamiltonian that we used to solve. Okay, then we have eigenstates. They are normalizable. That distinguishes them from scattering states. And very importantly, we will get back to this hopefully at the very end of this today's lecture. We find the following statement in every lecture on quantum mechanics. If you have an eigenstate, you can always choose them to be real valued. What this means is you will have no local phase. This is in any textbook on quantum mechanics, right? This has a profound implication in the context of QED, but this is just a standard result that everybody is used to. So remember, quantum mechanics, our eigenstates have no local phase. They can chosen to be real, unless we have a magnetic field, but that's just a static problem. All right, so we use this Hamiltonian now that has eigenstates. So we have a ground state, we choose 0 temperature, and then we can basically calculate the response of a single entity. So we now think really about a molecular gas or an atomic gas, and we calculate the response of a single atom or a single molecule. That's this piece here. What is the response is basically asking, how does the dipole of my molecule, a single molecule or single single atom, change if I put there an external field? It's of course time dependent. I do a Fourier transform, I get the frequency dependence. And that's again just the standard form that you definitely have seen in many textbooks. This is just a linear response kernel. But now you plug this in, into the definition for the E for ensemble, you can read it, but this is the macroscopic response because here it's now N over V. That's the local density, right? This is for a control volume, how many particles are there. So in this way, we assume that the microscopic response becomes the macroscopic response, okay? And this we can then plug into our absorption coefficient, right? Because a single atom will not absorb much. It goes with the macroscopic ensemble. And that's, again, the standard result that you will find in most textbooks of electronic structure and how to calculate an absorption spectrum. All right, so what I told you, either you have seen already in lectures or in my lecture notes, so it's something standard. But now let's scrutinize what we have done. What we have done is we have taken a microscopic theory for atoms or molecules and have connected it to a macroscopic theory, namely to the macroscopic response, and then to Maxwell's equation. And this is called the micro to macro connection. In other words, I could phrase it in a more quantum way. We did not calculate the wave function of the ensemble, right? Because in principle, I have a huge ensemble with very, very many atoms and molecules, and I should calculate this very large wave function. But it's of course out of the question that we can do that, right? We can not even solve the wave function for simple atoms accurately, or say at least exactly. It's very, very hard problem. So forget it for 10 to the power 20, 30, whatever molecules or atoms. So we make an assumption how this big wave function looks like. And the assumption that we took without making it explicit is a tensor product. They are all statistically completely independent. That's basically what I said before. We assume when we connect it to the Maxwell's equation that the microscopic response is equal to the macroscopic response. But do you think that this will always be true? Are all atoms and molecules independent? Definitely not, right? In a solid, it's exactly the opposite. And it's very, very well known, specifically in solid state physics, that the macroscopic response has nothing or has to do, but is not equivalent to the microscopic response. And we know this also from atomic and molecular physics. The moment we are not in the very dilute regime, the moment where our molecules and atoms get closer, for instance, they start to feel each other via van der Waals forces, or they start to build suddenly some other structure like in a solvent, then we have a different wave function. The way how we express it, because nobody can calculate this macroscopic wave function, is by introduce a new auxiliary object we call local fields. The logic is very simple. If they're closer enough, the particles, whatever that means, I take one particle out of my huge ensemble, then the rest will screen the field. And that's what actually comes in here. This is the simplest way to take this local field effects into account. This is called Clausius-Mosotti. And it exactly expresses this, that the other particles screen the field for the one particle. And in this case, you immediately see here plotted in green, the one where we say, in orange, the one where we say everything stays as microscopically, or if you increase the density, you will see quite a huge difference. And this is the first real problem, because we need to think about how we connect micro to macro, and this is exactly the Maxwell field. Specifically, if we talk about self-consistently, we need to think how does the microscopic description of our constituents, say of the solid, connect to the macroscopic scale, because our Maxwell field connects these two things. And this is, at least to our understanding, exactly the origin of the effects in polaritonic chemistry, because you can see small changes going from the micro to the macro scale and also acting back, right? So there's a very, very rich structure that we did not use yet in all our theories and also in experiment, only slowly learn that, of course, how the microscopic and the macroscopic scale work together is non-trivial. And very importantly, you have seen the issue that appeared here was that I made a choice. I made a choice and said, I think it's dilute enough. No, I think I should use this. There is no unique way. There's a lot of literature on this, but there's no unique way how to do this, because that would mean you have just suddenly solved a infinitely large quantum problem of a lot of interacting quantum particles, right? This is very, very hard. So this is the first problem, this scales connection. And Dominic will talk about implications for polaritonic chemistry then on Friday. But there's also another scale appearing. And this has to do with submicroscales. And this is again an example that I don't go through here in detail because it's in the lecture notes. But we can ask the same question now for a very simple meta system. This is just a particle. So this is an excuse for an atom. We have one electron in a harmonic oscillator. And we say we couple it. And I use the word naively, not to disparage the coupling, but just to say that there is more to coupling than just writing down something like this. And we naively couple it in this way, E dot R. And we do not take E as an external field, but actually as the field that is generated by the movement of your charged particles. So the solution of this Schrödinger equation goes in here in the inhomogeneity, gives you a current, and you solve the Maxwell's equation. Here again is a different form of the Maxwell equation. It's a vector. This is the second order form with vector potentials. So you calculate this from the time derivative, you get the E field, and you solve this equation self-consistently. You can actually do this analytically. It's in the lecture notes. And one important thing that one realizes is that irrespective of how weak the incoming field is, even if the incoming field is 0, you get a complete renormalization of your particle, right? So the statement that there is weak coupling because this is now purely a classical field is not correct. The effect is actually infinite, right? We have here the renormalized frequency, and we can do the calculation very easily. We actually have here a diverging term that diverges with lambda to the power 3, and lambda is a smallest scale, or rather a highest momentum. So we think until which scale does our electron actually couple to light? Gamma rays? I don't know what is higher than gamma rays, super gamma rays. Or is there at one point, does it behave differently? This is an ultraviolet regularization or cutoff, and you have to put it here. And what that means, it means several things. First of all, even though we have described our fields classical, the effect, if you treat light and matter self-consistently, is infinite. That's well known already from classical physics, radiation reactions. Further, we see that this coupling is not really correct. Why? Because we have here a minus sign. And you immediately realize if I choose to model here something weakly bound or say a free electron, then any coupling will lead to an inverted parabola, right? Because suddenly I have an atom that looks like this and it's unstable. It's an unstable theory. We will clarify in the course also how to properly couple if you go beyond perturbation theory. This type of coupling makes sense in perturbation theory. And a third important observation is we started out originally by assuming that we can couple in a linear way, in linear response. And the usual assumption that you read very often, not only in textbooks, but also in publications is if the incoming field is weak, we can do perturbation theory. But perturbation theory does not converge in quantum mechanics. That's a well-known problem. And this is what you see here. Does not matter how weak the incoming field is. Even if it's 0, this effect becomes infinite. So when we talk about light-matter interaction, specifically self-consistently, the effect of light is too strong. That's what is called the ultraviolet, the ultraviolet problem. We will get to that. But this is just an example that seemingly simplest problems like, oh, okay, can you tell me how this hypothetical atom absorbs at minus infinity frequency? That's a little bit inconvenient result. So you have a lot of problems here because it is seemingly two different theories. They don't tell you how to connect them. So yeah.
That's the lamp shift?
No. That's an instability because the coupling is wrong. The lamp shift would go up. There should be a plus.
Do you have the lamp shift on that level of theory?
Yeah, you have the lamp shift, but it goes in the wrong direction. And it goes in the wrong direction. So this is also well known from open quantum system theory. It's called Caldera-Leggett, and Caldera-Leggett wrote like a very extensive appendix where they basically showed, no, don't do this. Anyway.
But you could fix it. So you could add a potential term, right?
You add an R² term. No, you see where I'm going, right? Actually, if you will see that if you do the coupling properly, this minus will go away. And it cancels exactly. So this is wonderful. But for the moment, I just want to pique your interest. That seemingly standard things that everybody would tell you, yeah, and then you couple in this way, and then you this, and everything is known, right? Just linear response. That's not true. That's just not true. It depends on the level of theory. Okay. Let us see whether we can make heads and tails of these many problems. I just show you one problem. And let me first recap briefly. So traditionally, what we do is we describe light with Maxwell's equation. Maxwell's equations have very many different forms. I don't go into detail. There are really many different forms of it. You will also learn a further one in the next part. And already on the level of just classical electrodynamics, there's a very strong consistency between light and matter. It needs to fulfill the continuity equation, else your Maxwell's equation are unphysical. It goes back to locality in the end, because if you break locality on the matter side, also your Maxwell theory will become non-local, and you don't want that. We usually describe our matter microscopically with quantum mechanics and the Schrödinger equation. And very importantly, for this course or for this whole school, we usually assume observable masses and also observable charges. The charges, we don't need to care because we don't do Dirac, but we still need to care about masses and mass renormalization in these next few days. And you will actually learn yourself how to do it. And combining these two seemingly different theories lead to ambiguities. And there's no clear way how to fix it, unless you go a step back. Then also not everything is fixed, but at least you know where are snakes in the grass. All right, so this was a very brief and hard recapitulation. And I just wanted mainly to highlight that even for simple, seemingly very, very, very simple problems, like calculating an absorption spectrum, this is far from trivial. It's just we are used to employ it in situations where it really works and where we are sure that it works. Now, when we go to strong light matter interactions, we don't know anymore. So this is again a reason why an ab initio theory is convenient, because the usual assumption, the usual ideas, we have to scrutinize them. We don't know because the underlying theory has ambiguities. We need to be very, very careful what we do, because you really see a lot of statements out there in the literature that only come about because they are not aware that these standard theories also don't work, right? These examples that I show you, only very few people seem to be aware of them. But it's be careful. That's all I'm saying. So foundations of QED. So what we would like to do is to have a theory. Sorry? Ah, yeah, have you questions? Yeah, you can anyway always interject, right? I talk and blah, blah, blah. So the exercises will come a little bit later because, yeah, but please. I like to talk, as you might have noticed, so I will not stop unless you interject. So if I get tired or bored, just interject with a random question. Like, for instance, what is your favorite color? It's all good, right? It's a valid question. My favorite color is black. Anyway, so please, really, just it's not meant that I blah 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 and you listen. Secondly, also, I mean, I'm relatively fast because everything is in lecture notes. You will afterwards also get the lecture notes on the GitHub for this afternoon session. So if there are things that are not clear, please ask me. But you can also take a look because most of the details are there. Okay. Anyway, so where were I? Second part. So after having set basically as a new motivation, as a theory motivation that we should go back to the basics and understand where do these theories come from? Where does my meta sector come from? Where does my light sector come from? How are they combined? To basically understand these problems, and I hope at the end of the school you will understand where these problems that are shown you come from and also have a relatively good answer for it. So go back to the basics. Where do these theories come from? And the learning objectives of the second part is you should know basically afterwards how to derive the homogeneous Maxwell's equation. You should understand why we quantize the Maxwell's equation. And you should understand how we couple light and matter and why there is, I would say, one and only one way, at least to the best of my understanding. All right, this sounds like an easy task. Again, we will not write down the Hamiltonian. These are just bits and pieces that go in the assembly. So you can use the same thing for full relativistic QED or any other field theory you want. It's always the same logics. There's nothing that differentiates them. All right. So one thing, yes, another thing that is important. If you look into the textbooks of QED, there are very many different ways to derive it. Mostly the people just postulate it, but usually people use then a Lagrangian formulation. That seems fine for perturbation theory, but is problematic for a non-perturbative theory. There are different reasons, and in the notes, in the lecture notes, I explain a little bit why there are problems. I will not go into details because I will just choose a Hamiltonian route. But be aware that it depends already there whether you use a Hamiltonian or Lagrangian, where you might end up. All right. Hamiltonian route. So what is QED? QED is very simple. It's that. QED is just a relativistic dispersion relation. E is the energy. This is mass, speed of light, momenta. And QED, okay, it's not all, right? Because then I could stop here. And what QED wants to do is he wants to make this quantum. So what you do is you say, let's quantize this dispersion relation, this special relativity relation. And this is basically in most textbooks also done by saying, okay, now you replace. But let me point out that these simple errors here from the energy to the time derivative and from the momenta to the derivatives, spatial derivatives, there's an enormous amount of conceptual and mathematical details that are very, very important. These are not derivatives. These are self-adjoint operators. So it's very complicated functional analytic objects. There is a host of idea behind it because at the same time, this has to do with representation theory of groups, namely translations in space and translations in time. So there's a lot of conceptual, theoretical, and mathematical details there. Marcus, who will be talking tomorrow, will give you a glimpse of what can go wrong. But usually when you do standard quantum mechanics, you don't need to bother because mathematicians and mathematical physicists have made sure that you have to do a lot to break the good math. In the case of light matter interaction, we are not so on safe ground. So I take this step here just as to point out something that I always say. Not every formal manipulation that we as physicists or chemists do is mathematically allowed, and you can get complete nonsense. So be aware, we do it here without thinking, and we often do it, it's good, but be careful specifically in a situation at a non-standard whether such things are allowed or under which conditions they are allowed. Marcus might show you some problems there. Okay, so we just do this. We replace everything by these derivatives. Again, these are differential operators. And what you get out is this equation. Cool. Klein-Gordon equation. A next important thing that you need to realize when you build a theory, wave functions are not physical objects. Wave functions are auxiliary objects. They are just there to help you calculate physical observable. A wave function has no physical reality. So we have to test whether this wave function makes any sense, right? And one of the most basic, or the most basic condition we have in physics is that probability or equivalently charges are conserved. You cannot destroy probability, you cannot destroy charges. So we take this simple translation from special relativity and quantize it, so this Klein-Gordon equation, and we calculate the local continuity equation. So you remember in Maxwell's equations also appears in form of charges. Here it appears in form of probability. You just multiply here by charge, then it's a charge, local charge conservation, but this is really the most fundamental thing. And what you see is, this is inconvenient, we have suddenly probabilities that become negative. So this form of a quantum theory is non-local, and you don't want to have a non-local theory. You cannot work with this. This is the beginning of relativistic quantum mechanics, and people realized, this doesn't work. And the problem is the second time derivative. And this is a very, very, very important observation. This goes back to also what was said in the morning, that you can rewrite certain equations as first order or a second order equivalent. This will be important also in QED. Here we see the second order. Yes?
Can you explain the connection between the probability not being larger than 0 and non-locality?
Because you want to have local conservation of probability, and that would make you into a non-local theory. You would, your particles would jump around. That's it. All right. So the problem is the second time derivative here, second order equation in time. And then clever person like Dirac said, no, let's go first order. And what can you do in first order? Yeah, okay. You say, in order to get this relation, I just apply a first order equation twice. That was what he came up with. And of course, most of you or every one of you knows that, okay, if you use it for spin 1/2 and mass non-zero, you get Dirac's equation. But most interestingly, you can do the same trick for any spin and any mass. Yeah, I will tell you a restriction afterwards, but you can do the same trick now, for instance, for spin 1 and no mass. Spin 1 and no mass are photons. So let's do that. What happens if we use the program of Dirac for spin 1 and 0 mass? So we have spin 1 matrices. So we have 3 entries. So we talk about 3-dimensional fields. Already align a little bit with our 3-dimensional world. So these spins here, and then we follow the idea. We replace. Now we take a first order equation and also in time and p, and use here these spin matrices. And what we find is the so-called Riemann-Silberstein equation that already Angel showed you. So here you see this is exactly the same like in the case of Dirac. Instead of a gamma matrix, you have here, that would be for spin 1/2, you have here S, which is for spin 1. And I will explain in a moment, you have a side condition. That's very important to understand QED. In this case, for spin 1, you have a side condition. Let us briefly look into what this side condition means, please. Exactly. It tells us there are no longitudinal photons. So that's the first thing, because as I will show you, without this side condition, that means you only have transverse fields. Without these side conditions, photons would not fulfill special relativity. That's whenever somebody says there are longitudinal photons or time-like photons, they don't exist, because else you would violate special relativity. I will comment on time-like and longitudinal photons later on, what they mean or in which capacity they are used. But this is just the very basic results. There are no longitudinal photons. Okay, with the side condition, let's see whether we can reproduce this funny relation. And it's now important that we interpret this f. So here I used a small f. I didn't specify units, but here I specify units. And f perpendicular means transverse, like propagating waves, right? The units of a usual wave function, like the Schrödinger wave function. So that's a probability. Then I use two things. First of all, I use that s times or minus I s times the vectorial nabla gives you a curl. And this immediately explains you, and I found this for me very illuminating, the connection between spin and rotation. Because here it is really a rotation, because it's 3D, right? That's the spin of a spin one particle, right? So it's a rotation. And if I apply the rotation twice, then I have this relation, right? This is the vector identity, the Laplace vector identity that I showed before. Now apply it twice. I apply the energy twice to the Riemann-Silberstein, I would get the curl twice. And that would not be this thing here. I want to get p squared, right? That should be p squared. I'm missing a piece, this piece. So I cannot add this unless I have here a perpendicular. So only in the case that I get rid of 1 degree of freedom, which are the longitudinal ones, does this agree with relativity. So the side condition is very important, and you get the first quantized wave function for the photon. Super, right? Since you usually are not used to think about photons in first quantization, there is a problem, and we will get to it, right? But at this point, hey, we have done it. Now, if you looked carefully at this equation, you might have realized something. There's an h bar here and here, but there is no mass, right? Where's their mass? We said it's 0. In a Schrödinger equation or the Dirac equation, the mass hinders you on canceling the h bar. But here you can get rid of the h bar. Okay, let's do that. We give it different units, and you immediately understand why these weird units appear, because I just write this f tilde now in terms of E plus ICB. So E and magnetic field. And then plug it in, the h bar is gone. F tilde gives you the homogeneous Ampere and Faraday law, and the side condition gives you the Gauss laws. And voila, we have the Maxwell's equation. But now we are, of course, a little bit confused. Which one is the correct interpretation? The answer will be, we only know once we couple to meta. If you remember the Maxwell's equation at the beginning, the source term there, if the source term comes from a macroscopic theory and is on a macroscopic scale, then that's the right term. That's the right interpretation. If, however, the current and the densities come from a microscopic theory with h bar, then this is the right interpretation. So you see already here, we need meta to give our light meaning, or at least to set a scale, right? Please. For the Klein-Gordon? No. Starting from there. So the only thing I do is I say, I don't want to express it in the second order equation, but I want to express it basically by applying it twice. So what I want to do is, I would like to get something like this, p squared, c squared. And naturally one would say, okay, I go and say this is dt squared and this is basically something like this. This would be the Klein-Gordon equation. But Klein-Gordon says that I work with a scalar. And then Mr. Dirac said, nah, maybe I do it the following way, because if I make it here, basically I make first order, and I then combine it, I just get back the old one, right? I cannot do it. So what he then said is, we have to use vectors, not scalar wave functions. In our case, our wave function is three-dimensional. So that's why we then say, yeah, what we want to do is to get something like, and since I don't want to write something wrong, you say, you apply in this case F0. This is your RS operator, if you will, and you apply this RS operator just twice on F. That should give you back your E squared plus P squared C squared. But then you see you have to have the side condition that this is 0. That's basically it. I reintroduce. It's not like that I tell you that this is the only choice, because every spin gives you a different choice. But the only thing you want to do is you want to express this via a quantum theory. Yeah.
So this Riemann-Silberstein operator has non-diagonal elements, you can see. And if you apply it in the square, it's only diagonal. And so this square equation holds component-wise.
Exactly.
So this is the second order equation component-wise,
Yes,
while
exactly.
the first order equation is non-diagonal, but not component-wise,
Yes.
but only first order.
Exactly.
That's the relation between those.
Exactly. And the Dirac does the same. The Dirac equation is the same. If you apply the Dirac equation twice, you get this one with a mass. That's how the relation comes about. Does this answer your question? Thank you so much. Yeah. We'll get there. But again, action says you want to do a Lagrangian description. And there are reasons why a Lagrangian description is not very helpful in a non-perturbative theory. We can talk about this, but in principle, you have some issues. And the issues with the action is actually the Minkowski space. You don't want to go via the Minkowski space. The Minkowski space is not a Hilbert space, it's a pre-Hilbert space, or the vector space thereof. So you run into a lot of mathematical issues. So that's why the Hamiltonian route is a little bit easier, or mathematically better, so to speak. No, you can, but only perturbatively. And path integrals are mathematically, say, at least problematic. That's the issue. You can do it perturbatively, but not non-perturbatively. I will get to that. And you will also hear from Marcus tomorrow. This has to do with a lot of things. There is not one answer, but there are several ones. But give me just very briefly. First of all, you work with Minkowski space. The corresponding induced functional spaces are not positive definite, so they're not Hilbert spaces, so you cannot define operators. Secondly, you work with distribution functions. The distributions cannot be multiplied. The assumption in the path integrals, this is the next stuff, is that you have an infinite product. There is no definition of an infinite product, except in very special cases like the Feynman-Kac formula for harmonic oscillators. And that's the three major reasons. And I'm pretty sure there are many others, because 60 years of QFT have not solved this problem. Put it like this: you will have the same problem in non-relativistic quantum mechanics if you want to do it with path integrals. It's really the path integrals are not a good object to do non-perturbative theories. All right. So we have this different interpretation, and we learn that we have different interpretation, and it will be very important for the coupling again. Here already, I tell you, I need to couple to choose. And you will see that from the meta side, I have the same problem. Meta needs light to choose. So one thing that we, however, immediately learn from this macroscopic perspective, right? This is just Maxwell's equation. And if you go into the textbooks, the Maxwell's equation tell you, okay, the energy of a Maxwell's equation here given in terms of this Riemann-Silberstein, but it's just E squared plus C squared B squared. Positive integrand, the integral is positive, 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 positive. The energy of this thing is positive. Super. That seems reasonable. But we are interested in QED, so quantum. So we go with this one. So let us look. What does this equation tell us? We can solve this equation for the eigenfunction. So we know that the spin gives me a curl. The eigenfunction are nothing else than plane waves with a vector, basically a polarization vector. And the polarization vector is just exactly the usual one. Since there are no longitudinal photons, you have a K. And you have two polarizations that are perpendicular, 1 and 2. So these are the two solutions. And it's not an accident that the plane waves appear, because very importantly, that we'll also learn, the matter modes and the light modes need to agree. But that's just a side remark. You have here the exponential. So it looks like standard quantum mechanics, except of this vector polarization vector. You can also call it spin, right? In quantum mechanics, we always talk about spin up, spin down. This is basically the photon equivalent. That's where you have, we call it in photons polarization, but you could also call it spin. It's up to you how you call it. But the solution is a linear combination thereof with a phase. And what is it? It is circular polarization. So it's one that goes like this and one that goes like that, right? So these are circular polarized states. So these are the natural states of these photons. All cool, but we have a problem because we have positive and negative signs here. Exactly the same like with Mr. Dirac, we have negative energy solutions where there should be none, right? We know it should be positive. So what we essentially did was we start out with a second order problem, classically. We realize, oh, we cannot turn it into a second order quantum theory. So let's go to first order. Okay, we have solved one problem, but we introduced another one because first order problems give you negative energies. So we have to do a further trap, a further change, a further trick. It's a trick. It's not something where I say, oh, this is the only possible way. It is a trick that, however, due to Dirac was obviously very, very successful. You interpret now this no longer as a single particle equation, but as an equation for many particles. So you basically have anti-commutations relations, and you lift this single particle problem into a Fock space, which is also a Hilbert space, where you now don't fix the number of particles, and you introduce these annihilation and creation operators that follow this type of rules. And with this trick, why we use bosons, I don't have time to go into. It's in the lecture notes. You will see it's a brief calculation to see that you need to use bosons here. But then you see my energy is suddenly positive because it's just H bar A dagger A. And that's how we rectify the problem that we have negative energies. So it's very important, very, 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 very important in light matter interactions. Your energies should always be positive. If your energies get negative, oh, there's something fishy. And this was, of course, also the content of the first notebook, not for the quantum fields, but actually for a single mode. And so I don't know whether everybody did the notebooks, but now would be the time maybe to talk to each other. And if you have solved it, explain it to the others, or just to chat about basically this first notebook among your groups. And I think you can also get a coffee in the meanwhile.
ask one more question real quick? Are you quantizing Maxwell's equations just to test if the theory contacts matter the way we expect it to? Is that the reason?
Sorry?
Why are we quantizing Maxwell's equations?
Because of the positivity. If we wouldn't do it, then we would have negative energies. Second quantize. So you mean the first quantization?
Both.
Both. Very good question. Very good question. I think there are different answers. And for the quantization of the photon field, there have been a lot of previous indications. Like, I don't go into details. Usually, if you have different reasons why you do it, it makes sense. I just showed you one route that comes from special relativity. But if you go from thermodynamics, the Rayleigh-Jeans catastrophe, so the ultraviolet catastrophe in the black body radiation, was one hint that you want to quantize your photon field, because in this way, you actually could agree with experiments, right? So if you remember your thermodynamics, you have your bosonic partition function, and that dies down with high frequencies. While if you would have classical particles, you have equipartition, so all frequencies are equally. So that was one reason. This is one other reason. And then to my understanding, the third reason is the Gibbs paradox. So already in thermodynamics in the 1800s, they had the problem that that in the classical thermodynamics, they could not write down actually their partition functions because they had only integrals. And what they needed to do is they needed to introduce a smallest scale, which makes, of course, sense statistically, right? Because you make a statistical theory, so you make a theory that only tells you statistically what's going on. And there has to be a scale that it doesn't describe. So they introduced an H, which later on was named after Planck. And with this, they, for instance, solved the problem that entropy was not additive. So these were already indications that you needed to quantize basically your microscopic theory, or if you go to a microscopic theory. At least these are the three things that I'm aware of. I'm pretty sure there are others. Very good question. We get to that in a moment. We'll get to that in a moment. Yeah, well, all right. The break is officially over. Did anybody take a break? Okay. So did any or everybody of you finish the exercise? Or so I saw a lot of people do calculations. So we can just briefly go through the results. And you will get the results and also the solutions anyway. So you will get the full notebook that you can check, because the idea of the notebooks is that they build up a little bit on each other. So the solutions of this one and the solution of the next one are needed then to the solution of the third one. So if we just, no, I don't want to do it like this. If we just go up. Exactly. So I like this strategy more, thanks to Lucas. So the background is just the quantum harmonic oscillator, as you have seen, appears for various reasons. The way how we introduced it was due to positivity. I mean, this is one reason. You could also argue, as said before, about the quantization of the black body radiation to get rid of the Rayleigh-Jeans catastrophe, or many other arguments. But in the end, it's very helpful to be a little bit fluent, or have seen a few of the standard transformations that will become important or are used very often. And so what we wanted to do, because you will see that you will need this afterwards, is basically to diagonalize this Hamiltonian with this extra term. And in this second strategy, it just takes this very simple form, right? You just introduce a new frequency. And then, okay, usually the trick is, or how are the creation annihilation operators connected? This was also defined in the instructions. You do it by just dividing by h bar. In this way, in this case, it's omega tildes. And then you can rewrite the omega tildes in the old a plus a daggers. And in the end, well, you already see what happens here. This is now just an add-on to see how the B and B daggers look like. But in the end, you have it already diagonalized by defining this new frequency. And then you basically have the solution with this omega tilde. This is connected actually what Professor Kono showed. This is the steermagnetic shift. So basically the effect of the a squared term, this blue shift, right? Because your frequency, if this would be the frequency of your cavity, you can imagine this as, so this part actually could come from charged particles. You will see this later, and they renormalize frequency. Does this make sense to you, or are there open questions? Or put it differently, was it hard to do or was it okay? Okay, very good, very good. I see 3 people have done it. Very good. But again, we will put this online and then you can check again. And then the next one was basically similarly to add a further term. Now it's basically a shift. So we add a B plus B dagger. So it's now consecutive, right? Before we changed the frequency, and now we add something, right? You see that we work here with the tilde. You could, of course, also start with the original one and just add this shift. This is just a coherent shift, basically. So you can imagine you have a parabola and then you shift it somewhere else. So that's why not much changes. And you can essentially just rewrite it in this way that you just add this term to B. So C is then just adding these 2 terms. And then if you multiply, you see you just get this energy shift. And we will use this renormalization of the frequency and this coherent shift when we couple light and matter in the calculation. So you will just use these results later on, okay? So we can give it to you, hopefully, in one way or the other for the next notebooks. And then there are some addendum that you don't need to worry too much about, but it connects very nicely to what Professor Kono said today in the morning. You can calculate for the various modes how the electric field looks like, and then you can see what happens if I change my frequency. So due to the renormalization, what happens if I do this coherent shift? It's like you basically put charges in your one mode photon field, and then you see E is always 0, so the electric field, but E squared gives you non-zero results. So these are the vacuum fluctuations of this very simplest thing, the single harmonic oscillator, interpreted as a quantum mode. All right, so let's get back. So at least in this way, how I present it, and again, it's important to stress, this is one way to derive these ideas. It makes a lot of sense to me. Doesn't mean that it should make a lot of sense to you. There are very many different ways to get to the same conclusion, and it depends a little bit on your personal preferences, what you deem more important, less important. Luckily, there are very different ways to get to the same result. You have to find the one that makes most sense to you. I present the one that I find most clean. That's a personal choice. All right, so we have now second quantized everything. And I just repeat, before we get there, we started out with a quadratic dispersion relation to actually fulfill special relativity. Why quadratic? Because we want to make sure that we have a maximal velocity and so forth and so on, so a linear relation wouldn't work. Then we quantize it and we realize we cannot do it in second order. We have to go to first order, first trick, but then we see we violate positivity, so that's why we do a second quantization to enforce positivity. Now, I highlighted that there are no longitudinal photons, and time-like I will explain a little bit later, or maybe now in the next step. So these are type of photons you sometimes hear or see specifically in the context of high energy physics. And as always, since there are different ways, you might wonder, what did we do in this type of quantization? How does this look like in a slightly different form of the Maxwell's equation, right? As I said, there are different forms of Maxwell's equation in terms of E and B fields, in terms of displacement and magnetizing fields, or in terms of vector potentials. Because what we did by starting from the first order equation, only keeping the physical degrees of freedom and quantizing the first order equation, if you write this in terms of a vector potential, that's equivalent of doing the Coulomb gauge. The Coulomb gauge does exactly the things that we do here. It's a very, very natural choice. I will again comment on the reason why in high energy physics it's not so much used, but you see it is very natural because it only keeps the physical degrees of freedom. It doesn't introduce other degrees of freedom that you do not want to have, like longitudinal photons that would break relativity, right? So under the hood of all that I've shown you, in parallel, of course, there are very many reformulations. In parallel, we have also quantized all the other reformulations up to some math problems, because these transformations are sometimes not well defined specifically when you work with these operators. But formally, and if I use the term formally, I mean I ignore all mathematical problems, because there are always mathematical problems. If you quantize it in this way, you quantize it also in the other ways. And what you see is the vector potential that we have chosen here is Coulomb gauge. And what that means, this is the classical form of the Maxwell's equation. We have no charges, right? This is a free theory. There are no charges. So this is basically Ampere's law. And what you see, these other parts of this vector potential form, they would consider transverse fields, which then would give rise to longitudinal photons. They're gone. These would be the time-like fields. They're also gone. And it also implies here, I crossed out everything, it implies if there are no charges, then there is no vector potential. That's also a condition from Coulomb gauge. Other gauges would say, I have no charge, I still have a vector potential. And that's, of course, inconvenient. So this is under the hood of what we just did. Again, remember there are very many formulations, and this formulation will become important once we couple to matter. Right? I only talked about light now. Please. Because there are no charges. Right, we get to that. Of course, the moment you couple to matter, they are charged. But this is a free theory. So let's couple to matter. Again, I don't go into detail why Dirac is a problem. I will comment on this tomorrow. It makes more sense. We define our matter sector. The good thing is that a little bit simpler Schrödinger theory has all the same ingredients as the Dirac. So everything I say here is equivalently correct for Dirac. But what we do here in the first step, we do, of course, the same. Quantum theory is all dispersion relations. These are our basic excitations. And of course, in principle, we would also like to have everything relativistic for charged particles with a mass. But now we make this approximation even before we quantize. We say, we make non-relativistic approximation of this relation. And then we follow the rules. Again, in the quantum mechanical setting, we're a little bit safer. There are not so many snakes in the grass. And we get to this equation. This is the Schrödinger equation that you might have seen. And I would like to ask you to look at the second notebook. And I hope it's a little bit faster. Just that you briefly repeat your knowledge about just single particle, a free single particle following the Schrödinger equation. Because at the end of this lecture, you will look at coupling one mode to one particle. This is not yet the full theory, but you will learn how they talk to each other. So the notebook 1 was about the quantum harmonic oscillator. The notebook 2 is about, well, a simple one-dimensional Schrödinger equation, if you will. And the first question was, what is missing? And this is very, very important since we talk about operators. Probably you have immediately realized it once you went to the next question. But the point is here, and this is something that is very, very important. Again, I like to highlight math consistency, and it really helps you to avoid pitfalls and to not get to wrong conclusions. But this connects to the statement going from P to minus I h bar dx is not just a derivative, but it's an operator. And an operator has certain properties. Marcus will talk a little bit more about it, I presume. But in the end, you know from standard quantum mechanics that you want to have real eigenvalues. This, again, has very deep implications that come, again, from different theories, mathematical and physical. But in the end, if you have a finite area in which you look, you have to choose boundary condition. And in infinite space, you have to choose normalizability condition. That guarantees you self-adjointness, meaning real eigenvalues. So in this case here, you just need to make sure that the derivative acts on both sides in the same way. And that's basically done by periodic boundary condition. And that will be a second setting for our calculations that we will usually do. We will usually assume, for simplicity, that we have periodic boundary conditions, because that makes the calculation sometimes easier. And if we have periodic boundary conditions, we have eigenstates, so they're normalizable, and so forth and so on. So these are just plane waves, but now on a finite area, or in this case, a finite line. So that's all good. So then you just look at the dispersion relations. So calculate basically the eigenfunction. These are just the usual dispersion, right? That you get. You have here the mass appearing of the particle. You would call it, without coupling, the observable mass at that moment. And then you have its momentum k squared, right? And then there was the final question, which is numerical. I don't know whether you did any numerics there, but let me just tell you what comes out. If you do this, if you make this discretization, this second order finite differencing, you will see something.
One more quick question about the plane waves. Okay, I'm probably just forgetting basic quantum mechanics, but how do you have an L2 normalizable wave function if it plane wave throughout all of space in periodic? I thought that was required. The solution to the Schrödinger equation needs to be normalized. No? Can I ask another question from back here? I'm still trying to make sense of all this, because I mainly do electronic structure theory, where I just write down the Hamiltonian with Coulomb interactions for matter particles. And that's usually the assumption that I start with. But now it seems like you're telling me the Coulomb interaction emerges from the electromagnetic field in some way. I'm trying to make sense of that. Like, what is the real first principles theory that ultimately gives us Coulomb interactions?
This one. Of course, I'm biased, but you will see, and this is part of the whole lecture notes and also of the whole thing, you will see how the Coulomb, in the usual Coulomb Hamiltonian reappears. We will write down tomorrow the Pauli-Fierz Hamiltonian. So I was just giving you, I didn't give you anything except of the ingredients, right? So you will see that we'll get a Hamiltonian that looks almost the same like Coulomb, like the usual Schrödinger Hamiltonian, with a few add-ons. That's it. but it is designed in such a way to exactly recover electronic structure, because we don't want to redo everything from scratch.
Wait, so the only assumption behind matter is that you have free particles. Everything else comes from electromagnetic field.
Yes,
Everything?
exactly.
Wow.
Exactly. On the scale, because at one point there would be QCD, but we don't care about quark gluon plasma so much, I guess. Yeah, perfect. Should I give you still some time, or should I show you the answer? Because at one point we should have an aperitivo, right? So you get drinks and stuff. So I don't know whether it's time to get drinks and stuff. So I don't know, you tell me. Okay. You will get this stuff all online. I will put it online as soon as possible, or together we will do so, because tomorrow we will use it. So it would be good, at least at one point, to take a look at it again. Okay, so what we did is basically the following. So this is the Hamiltonian, and this is not yet the full coupling Hamiltonian, because dipole approximation and blah. I will explain these notions again, right? But you will have seen this P minus A. Here is not a minus because the charge is negative. That's why we always make an absolute value to, because sometimes it's not clear is if there's only E, if it's plus or minus. So that's why we do it like this. So this is P minus A. That's basically what we have just derived, but without the position. So this is called long wavelength dipole approximation. We will discuss this a lot, because this will be a very central topic, when to apply and when not. And then this one harmonic oscillator. So this is a ZXQs for a coupled system, because it's 1D, but actually you can